Welcome to The Explainer. Today, we are opening up the ultimate cosmic detective story. We're pointing our magnifying glass at a world that honestly seems to defy the very laws of planetary formation, and that's Mercury. For decades, scientists have been totally baffled by its bizarre, incredibly metallic internal structure. It has this massive iron heart, yet its surface tells a completely different story. It's a puzzle of epic proportions, and we're going to walk through the brilliant, painstaking scientific detective work that is finally cracking the case.
Okay, let's dive into this. Why is the closest planet to the Sun also the least understood in our entire inner solar system? It highlights a massive knowledge gap in our understanding of our own cosmic backyard. We know more about Mars and Jupiter than we do about this tiny, sun-scorched world that's just a few stones throws away, in astronomical terms. Why? Well, because getting there is incredibly hard, and what we find when we actually do look closely just raises even more questions. So let's look at the evidence. Section 1. The Solar System's Oddball, Investigating the Cosmic Crime Scene. Every good investigation starts by surveying the crime scene, right? Mercury is dense. It's actually the second densest planet in the solar system, right after Earth. And its massive bulk density has long suggested that it must be heavily enriched in metallic iron compared to its neighbors. So before the Messenger spacecraft arrived, planetary scientists naturally expected to find a surface mirroring that dense iron core. Instead, Messenger's X-ray and gamma-ray spectrometers found something shocking. The surface has only 1 to 2% iron. But wait, it gets weirder. They found an abundance of sulfur, around 4%. Sulfur is a volatile element, meaning it vaporizes really easily at high temperatures. Finding this much sulfur on a planet that practically skims the surface of the sun is just completely counterintuitive. It tells us Mercury formed in a highly reduced chemical environment, which drastically altered how its iron, sulfur, and silicon separated during its formation.
Section 2. Clues to the core. How do we map the inside of a planet? Now, what's really interesting about this next part is transitioning from surface chemistry to deep planet geophysics. How exactly do we map the inside of a planet when we can't even drill past the crust of our own Earth? We have to use clever physics. The key here is the moment of inertia. This essentially measures how mass is distributed from the core to the surface. Think about spinning a raw egg versus a hard-boiled egg on your kitchen counter. The raw egg has liquid inside, so the solid shell spins somewhat independently from that sloshing liquid interior, making it wobble and spin a lot differently than the solid hard-boiled egg. By bouncing radar off Mercury from Earth, scientists measured tiny wobbles in Mercury's 88-day orbit. And those tiny wobbles prove that Mercury's solid outer shell is physically decoupled from its deep interior. Meaning, just like that raw egg, Mercury definitely has a molten liquid core.
Section 3. Modeling a metal monster. Running the simulations. Knowing the core is at least partially liquid is only step 1. Now the computational heavy lifting begins to build a profile of this metal monster from the inside out, and this brilliantly illustrates the process. Researchers essentially throw millions of possible internal configurations at a giant computer. They mix different amounts of iron, sulfur, and silicon, an FSSI core, varying all the layer thicknesses and densities. The computer then filters out everything that doesn't perfectly match Mercury's known mass, radius, and that crucial moment of inertia wobble we just talked about. The remaining data points show us the highly probable structures of the planet's interior.
When we filter down to those most probable structures, the suspect profile is staggering. The liquid core's outer radius sits at roughly 2,020 kilometers, while the solid outer shell is a mere 410 kilometers thick. This is incredible. It means Mercury's core makes up about 85% of its entire radius. Compare the densities too. The material above the core boundary is about 3,300 kilograms per cubic meter, but below that boundary, it rockets up to nearly 7,000. This proves just how disproportionately massive and incredibly dense the planet's core is compared to its remarkably thin, rocky outer shell.
Taking all those overlapping data points, we can actually narrow down the boundary between that thin, rocky mantle and the massive metal core. What this data strongly suggests is that Mercury doesn't just have a simple iron core. Because of the sulfur and silicon present in the mix, it likely has a buoyant, solid iron sulfide layer sitting right at the very top of the liquid core. It's a complex, multi-layered metal monster.
Section 4. The Bepi-Colombo Mission. Dispatching the Special Task Force. We have the suspect profile, but we need final proof to close the case. Enter the European Space Agency and their epic special task force dispatched to finally unlock Mercury's remaining secrets. 4,100. That is the massive launch weight in kilograms of the Bepi-Colombo spacecraft. Imagine taking a 4-ton, highly sensitive scientific laboratory and herding it into the single hottest, most radiation-baked part of our solar system. It is an absolute marvel of modern engineering just to keep this thing from melting, let alone conduct precise science.
And the journey is just as staggering as the destination. Launched in 2018, it takes an agonizingly complex 8-year cruise to get there. To catch Mercury, Bepi-Colombo has to perform 9 complex planetary flybys just to bleed off enough orbital energy to enter Mercury's gravity well without shooting right past it into the sun. And look at where we are now. Arrival at Mercury orbit is set for November 2026. That is literally just months away. Routine science operations are going to kick off in early 2027. So the crucial point is what they are aiming to accomplish once they actually arrive. The mission's 2 distinct orbiters have some fascinating key targets. They will investigate the origin of actual water ice hiding in permanently shadowed polar craters on a planet hot enough to melt lead. They're going to map the source of Mercury's magnetic field, figure out the composition of the strange hollows pitting its surface, and of course definitively map that exact core mantle boundary we've been theorizing about.
Section 5. Unlocking Mercury's secrets, what it means for us.
Let's pull back from the specific data for a moment and see how this builds. Why are we throwing tons of metal and decades of human effort at this little scorched rock? The European Space Agency puts it into perspective perfectly. Bepi-Colombo will be the second and most complex mission ever to orbit Mercury, more difficult for an orbiter to reach than Saturn. Think about that for a second. Saturn is over 1 billion kilometers away in the freezing outer dark, yet orbital mechanics make reaching Mercury, right next door, actually harder. It beautifully illustrates the extreme lengths humanity will go to for answers.
Which brings us to our final thought. If Bepi-Colombo finally reveals exactly how this bizarre metal monster formed, how it got that huge core, the sulfur, the ice, what does that mean for the history of our entire solar system? Because Mercury is the extreme end member of planetary formation. If we don't understand how the planet closest to the sun was made, we don't truly understand how the Earth was made either. Keep your eyes on Bepi-Colombo as it arrives in 2026. The real cosmic detective work is just about to begin. Thanks so much for joining me on this explainer.